So today we'll be discussing the traveling salesperson problem, that is TSP, using the k-opt algorithm. So the prior knowledge is just some high school combinatorics and some basic knowledge of Python indexing. If you don't have the fundamentals, that's okay. With regards to Python, I'll place some links in this description below. So the TSP problem is also known as the traveling salesperson problem. So we have a list of endpoints, and our goal is to find the shortest possible tour that visits all the points and returns to the starting point. So this is just examples involving 4 nodes of tours for the TSP. So how the k-opt algorithm works, we have a tour, we delete k edges. We reconnect the tour so that the length is reduced. If there's no way to reduce the total length, we keep the original edges and we repeat steps 1 and 2 until the tour length can no longer be reduced. So we'll let dij be the distance from node I to node j. For simplicity, we will assume dij equal dji. So that is the direction of the edges do not matter. So far we've been using directed graphs. From now on, the edges will be undirected. However, let's say if the distances are different in both directions, you can still apply the k-opt algorithm. So we're just going to go through the steps. So suppose we delete edge v4, v1, and edge v2, v3. We'll end up with this thing over here. So the current length of the graph on the left is d12 plus d23 plus d34 plus d41. So if d14 plus d23 is greater than d13 plus d24, we will add the edges v1, v3, and v2, v4. Otherwise, we'll keep the original tour. So one important thing to note is the edges should be disjointed. So if the edges deleted are not disjointed, then we'll end up with something like figure 1. Now, if we connect our V1 to V3, we're going to have a subtour, and in this case, V2 isn't included in our tour, and that's a bit of a problem. If instead of connecting V1 to V3, we connected V1 to V2, then the only other possible edge connection we can make is V2 to V3. However, this is just our original graph that we had earlier. So we haven't learned anything new. So how are we going to represent our tour? So one way is to just represent the tour as a list. For simplicity, we will omit the last index. So we'll have 1, 2, 3, 4, 5. Now, one thing to note is there's cyclical symmetry. So if you sift all the vertices one across, the tours will still actually be the same. So for tour 1, we can see there's an edge going from vertex 5 to vertex 1. And over here in tour 2, we can see there's still an edge from vertex 5 to vertex 1. So this is the pseudocode for TrueOpt. So we have a for loop for I, for loop for j. So the for loops, they let us go through all the possible combination of edges. Obviously, you will need to make sure the edges are disjoint. So over here for 201, we have our vertex I minus 1 going to vertex I. We got our vertex j minus 1 going to vertex j. So the vertex will actually depend on the value inside the tour, but for here, we're just referring to the indices as the vertex. Now, if we can delete the edge from I minus 1 to I, and likewise the edge from j minus 1 to j, by reversing tour I thrice I colon j. And to do the reverse, you just use colon minus 1. We choose the best tour and continue until the tour can no longer be improved. So for tour, there are two pathways that need to be considered, tour 1 and tour 2. For 3-op, the tour will be broken into 3 segments when the edges are deleted. So over here, we got the expression for tour, where we keep the original edges. So over here, tour colon I, that's one segment, and that goes along with tour k colon, because the tour wraps around. Tour I colon j is also one segment. Tour j colon k is also one segment, and that's how we get our 3 segments. We will keep tour colon I and tour k colon fixed to remove circular symmetry. So there are 2 possible things that we can do. One would be reverse a segment and use colon minus 1, or you can permute the segments. So over here we swapped j colon k with I colon j, if you compare that with the original tour. So a couple things to note. There are 2 segments that are not fixed. One of the segments is. Therefore, the number of permutations is 2 factorials. Likewise, there are 2 segments that can be reversed. Hence, there are 2 to the power 2 ways to reverse the segment. So this lists all the possibilities, where NR means not reversed, R means reversed. From the rule of product axiom, we can see there are 2 factorial times 2 to the power 2. So that means there are 8 possible tours that we need to consider. If a tour has k edges deleted and the edges are disjoint, then there are 2 to the power k minus 1 times k minus 1 factorial ways of reconnecting the tour. And this comes about from the same approach that we use to determine the number of tours for 3-op. So using the same approach, we can prove this theorem. So this is the general pseudocode for k-op. So we have the for loop. Again, the edges need to be disjoint. Now, one of the key things to note is that we have a variable number of for loops. So to implement this is a bit difficult, but as it turns out, if you do a bit of Googling, there's a way to do so using our recursion. Anyhow, so we construct all the different possible tours as we discussed above by reversing and considering the permutations of the segments, choose the best tour, continue until the tour can no longer be improved. So just some technical notes. Note that 3-op is not guaranteed to outperform 2-op. So the reason for this is that sometimes 3-op can get unlucky and get trapped in a local minimum, while 2-opt might be able to avoid getting trapped into that local minimum and find a better solution. Generally speaking, though, we would expect 3-opt to outperform 2-opt because 3-opt includes 2-opt. For the algorithm we described, the edge from the last vertex to the first vertex in the tour is never deleted. To fix the issue, we can write the tour as follows.